and my daughter's at. And I realized what it was like to be a teacher. Not for me. I do not want to watch that many kids. That's awful. Kids are the worst.
So they're to play chess, teach chess, not to babysit.
Exactly. That's what I kept. I mean, some of the kids were like clearly not there to learn chess. So it's like, okay. So, yeah, really the worst. Like one kid was really just kind of like not there for chess. And I was just like, you're not here for chess, so why don't you just go down to the Boys and Girls Club, whatever. He like peed in his pants. And I was like, we get somebody here who like to take care of this. Like, I am not here for this. Yeah, I would not do well. Yeah, no emotional. I don't care. All right. So how was everyone's happy Valentine's Day? I brought chocolates, but I didn't bring them up. So sorry. It's the thought that counts. Right? I'll bring them in next time. I'll get another. So I hope everyone's happy. I don't have the exam written yet. I'm going to try to post it tomorrow. And sorry, one second. So I'll try to post the exam tomorrow. I think probably next Wednesday. Take home exam. So, I mean, the idea is I'd like you guys to be able to not do it with like an exam with other people. That's kind of the key. At open book, I don't care if you use your book or notes or whatever, but just, yeah, like let it be your own work. Okay. That's honor system stuff. And I mean, if I get answers with no explanation that are the same as other people's, I kind of get a little suspicious. I'm inclined not to give full credit for such things. So what I would like is if there's a question that you give reasons for your answers. So that's the way I can verify that you're actually understanding, even if you're copying, at least understanding. Don't copy. So I did grade the homework last night from last week. I noticed, so there was this problem that I'll talk a little bit about. It's not so easy, I don't think. So we can talk about it. But there was a bunch of people answered some questions on that, and I don't think I want to explain something. So there were several questions about like asking you guys to produce spanning trees of given graphs. Okay, you guys remember that? No? Any of the questions? It was so long ago. Okay, there were a few questions about, hey, give us a spanning tree for a given graph. And I received many answers. I would say almost half the class gave me an answer of a list of the vertices as the answer to that kind of a question. And that doesn't have enough information for me to produce a spanning tree at all, right? So like, let me give a simple example. So let's say I have this tree, or this graph, pardon me. Set this graph, label the vertices. I say, give me a spanning tree of this graph. Answers I've been seeing with several homeworks were this. That was the answer. Well, a list of vertices is not a graph, right? A list of vertices is just I mean, it could be a graph of a list of vertices with no edges, but it's not really a graph. I mean, it's just vertices. So what I need in addition to that are the edges. If I just get the vertices, I don't have any graph. I just have the vertices, no edges. And a spanning tree is really a tree. So it's connected by edges. So I need to know where those are. So you could do that, and that's acceptable. If someone gave me like, yeah, something like AC, BC, CD, that's a spanning tree. But I don't need you to do that. You can also just draw the picture. I mean, I'm fine with just a drawing. Like I don't need you to list out the edges if you don't want to. But I just want to emphasize that you really do need more than just that. All right, good. Then there was this question 34C, which gave you this graph, which I reproduced and asked for this question was it C or A? I don't remember if it was C or A. It was one of them. It was sort of how many spanning trees are there of this graph? And I think that's kind of a tough question, honestly. I don't think that's like an easy. I mean, you could. It's not hard in that you can write them all out, but that's not really the way you want to do it. Nobody really gave. Several people got the right answer. Not everybody, but I didn't get any real explanations. There was one that kind of gave me the best explanation. But here's how you answer this kind of a question. So what you want to do to find a spanning tree of this guy is I want to get rid of any kind of circuits, right? So spanning, one way to think of a tree is it's connected and it has no circuits. So this graph has some circuits in it. And so I want to get rid of them. So one circuit I see right away is this circuit here. I see that circuit. So I cannot have that circuit in any spanning tree. Right? So what I need to do, I need to eliminate that circuit. So I need to eliminate one of the edges, at least one of the edges in that circuit. So let's start. We'll just take it edge by edge. So let's start, and we'll say we can eliminate this edge CI. So if we eliminate CI, counting now. Eliminate CI. Well, then now does anyone see a circuit in this graph that's left? Yes or no? No circuits? Yes, circuits. There is, or how many say there is a circuit in this? Okay, 5. How many say there is not a circuit? Huh?
I said I'm
Present. You abstain. Choice of view. Okay. Well, there is. I can see one. Say. Not counting FA. I didn't understand you. F. Yeah, so a circuit is not necessarily the entire graph. It's just any path that comes back to itself. So yeah, so it's not an Euler circuit. I think that's what you're looking for. Yeah, it's not an Euler circuit, that's for sure. Okay, so but it is a circuit. And so we need to, and for this to be a tree, to get rid of more edges to get a spanning tree, we need to not have that circle, which means we need to get rid of one edge from this guy. If we get rid of one of those edges, any of them, we'll get a tree. Do you agree? So how many edges are there? I count 1, 2, 3, 4, 5, 6, 7, 8. So 8 ways of getting a spanning tree after I eliminate CI. Okay. And now, I have to consider what happens if I did not eliminate CI. So here I eliminated CI, and I counted all possible ways I could get a tree. Now let's say I don't eliminate CI. But remember, I have that loop. I need to eliminate one of the edges from that loop. Not loop, pardon me. So I had this circuit I started with, and I said I need to eliminate one of those edges, and I started with CI. Well, now let's say I eliminate any other one of them. So let's say BC. So let's say I eliminate BC. The same argument will apply for any of these. If I eliminate BC, do I have a circuit? Yes. Do we see this hexagon here? This is a circuit, still a circuit. So I need to get rid of another one of those edges. Well, I already dealt with all the possible cases of when I eliminate CI. So I'm not going to eliminate CI because I already dealt with I already counted all of those cases. So I need to eliminate any of the other edges in that circuit besides CI. If I do that, do I get a tree? How many other cases are there? How many other edges are there? So I see I in that circuit that I can eliminate. 5, right? So there's for each of these, for each edge, BC, BK, or KI, IK. There are 5 edges, 5 possible span, each obtained by eliminating one of those edges of the hexagon except CI. But that's it. Those are, we just covered all possible cases of eliminating an edge from that circuit, that square circuit here. We covered each one of those, and we know that any spanning tree, we're going to have to eliminate one of them. So we counted all of these spanning trees. We got 8 here, and then we've got 3 possible cases here, each of which have 5 possible spanning trees. So that's 3 times 5. So the total 8 plus 3 times 5, which is going to be 20. So one person, I think, maybe more than one, but I only really noticed one person writing this equation down, which I assume they got from this kind of an argument. Is it clear? Yeah. Question? Yeah, absolutely. So, I mean, one thing you can do, you just delete one. So, as I said, any of these edges, if you delete any of them, you'll get a spanning tree. And I'm just not deleting this one because I covered that up here. I already did that up here. So I don't want to overcount. So, but we can choose any of them. So if we did that, we get a spanning tree. The whole thing is a spanning tree. What the whole, what I have here, this is a spanning tree. It's a subgraph of the original graph up here. And as you can see, to be a spanning tree, you need every single vertex to be a vertex of that tree. That's the spanning part of a spanning tree. If I just took this tree, it would be a tree, but it's not spanning because it only hits 4 vertices of that graph. So a spanning tree has to have all of the vertices. So that's why when I got answers like this, I was like, well, okay, now, where are the edges? Has to have all the vertices of the graph to be a spanning tree. So of course, if you have a disconnected graph, there are no spanning trees. So there has to be a connected graph. Other questions? Out of the exam? I want to say, out of all of the things we covered, the most mathematically interesting thing is spanning trees. Like by like miles, like way more interesting than all the other stuff. Like mathematicians actually talk about spanning. Like I've been in talks about. Yeah, we don't talk about spanning. Or any of this stuff. It's fair, you know, I mean, I understand, like, everybody has their own taste. Yeah, see, there's that too. Well, guys, I'm not gonna take any of that personally. This is, you know, look, this is all like an exercise in, I don't know how to view this class. It's like you're coming in, we got some puzzles, we're gonna do some puzzles, you're gonna go home. You're gonna move on with your lives. Everyone's gonna be happy. It's gonna be easy, fun, and you're all gonna do well. Just put a little effort in. And you can hate spanning trees. It's okay. I love them. They're beautiful. But you know, you're wrong. Is what I'm gonna say. They're great things. But I'm gonna convince you it's okay. So scheduling. Let's get back to schedule. We're not done scheduling. So I do want to finish up that chapter, and that way we'll have all of the module 1 done before the exam comes out. So let's see if we can't remember where we left off. So we have all of these different things involved, all these different ingredients, actually a very rich picture of creating a schedule. We have processors, we have tasks, we have precedence relations, and we have processing times. I put all these together in different ways. The 2 main ingredients that we talked about, people can tell me, what are the 2 things? You could give me more than 2, but what are 2 of the things that we need in order to kind of algorithmically write down a schedule? We need the task. So let's write down these things. We need tasks. We need to know how many processors we have. Otherwise, these tasks come with processing times. So let's say we're given all these things. And we need precedence relations. Given all these things, what are like the sort of main ingredients with these things in mind that we want to bring into the story to kind of digest this information and create a schedule? We need that's one of them that I was thinking. We need to make a priority list. It's just a list of our tasks. And when we're actually converting that priority list into a schedule, we need to consult something. What is that we consult? Diagram. Nice. I don't remember is also correct. So we have, and this is a diagram of the precedence. We can consult these two pieces of information and create the schedule. Okay, good. So the key thing that we got through all of this, and now the last sort of ingredient is to create the right priority list, right? That's the last ingredient. Once we have these things, we can write down a schedule. So the idea is, what is the best way to create this? What's the best way? The answer is nobody knows. Mystery, one of the great mysteries of life. Let's schedule things. Like really, like there's not an optimal outcome that's efficient. Cool. It's always cool when you come across something where you don't know. It's like, I don't know how you guys feel about that. That's one of my greatest joys. Being confused. Then you get to think, like figure things out. Right? I'm pretty sure all of us are confused right now. There you go. See, this is a great class. My job it's not my job to confuse you. Oh, put that on the evaluation. All right, so okay, so what we did last time is we talked about a descending or decreasing time list, priority list. So we did give ourselves one recipe, right? One algorithm. That was really easy. Do you guys remember that? Right? We have a bunch of tasks, we look at their processing time, and we just order them in decreasing processing time. You guys remember that? That's not hard. We all can do that. However, that one is actually, practically speaking, generally bad. It will sometimes work. So it's a way of doing things, but more often than not, you will not get the best, an optimal schedule. So there's a better approximate algorithm, and we're going to talk about that today. And we started talking about it last time. So last time, in order to talk about it, we needed to define a couple of things. So we talked about critical paths last time. Let's see if we can remember what those are. So if you're starting out of, there are two different notions here. One is a critical path starting at a vertex, starting at X. What is this? Critical path is what? Let's say we have a digraph coming from precedence relations. What's a critical path? Right, it's exactly, it's the longest time path. I'm just put longest processing time path. It's not long in terms of graph, the length of a path. It's long in terms of, I add up all the processing times along the path, I get the longest time. Next to N. And that's for a path, and then for the whole graph, the graph is the critical path, start to end. And the is not really there. Speaking of Russians, right? You know what I'm talking about? No? None of you have studied any Slavic languages? Oh, BS, yeah. They don't have like definite articles. No the. So, what do you mean by that? There could be seven, right? There's not a single There could be one, but there could also be many. Depends on the situation. All right. So the first thing we want, so last time we talked a little, we gave some examples with this graph of a critical path. And what we would like to do, this is in the world of all possible graphs, this is a very simple example. So you may be given a situation where you have a very complicated example, and you would like to be able to find critical paths and find a critical path of the entire graph. So what we want to do is give ourselves an algorithm to find a critical path. This is called backflow. I guess they call backflow algorithm. Finding critical paths. So, all right, so what do? You start at the end, okay? One. So starting at the end, work backwards. Start at the end. Work backwards. Against essentially the orientation of the digraph, by looking, I'll say, looking at all vertices. Which yeah, actually, let me I'm gonna fix this a little bit because I don't like the way I've written it. So if I start at end, since I want to repeat this step, I'm also going to say or X. We'll look at all vertices Y, for which Y for which we have a directed edge like this. In a graph. And choose the one with the largest processing time. Largest. I'm mixing. Okay. Like this. Choose the one with the largest processing. On processing time, critical time. We'll do an example. Hopefully, it'll clarify my poorly. Critical time. And let's call that critical time L. So they do in the book, I think. And step 2, sine X. Time T plus L if X processing time T. And then step 3 is to repeat until you get to start. So let me illustrate. I think it's going to be easier to see how this works rather than my poorly phrased explanation. Okay, so the critical path starting at end is going to end at end. There's nothing going on. So we assume there's nothing going on here. So we're starting at the back, which is n, and we're going to work our way backwards. So now we look at F1, G2, and H3, these three. So these have processing time. These have critical times, which is the amount of time it takes to do this task and go to end, which is just their processing times. That makes sense? If I were at this stage, F, I would do it. It would take me 1 hour or whatever, and then I would be done. So this critical time is 1, this critical time is 2, and this critical time is 3. So it's the same as their processing time. Now what the backflow algorithm tells us is to take our vector, our vertex X, which we'll say is D, for example, something right before the ones that we've already done, D, and look at all of the tasks that are after D, which are F and G, and choose the largest. So the largest in terms of critical time. So that's 2. So then what we have here is that D is going to have processing time equal to its, or critical time equal to its own processing time plus that largest number 2. So what we'll get is, we'll get the number 3 here, because this is 1 plus 2. Similarly, for E is incident to G and G and H, which have critical times 2 and 3. And 3 is larger, so we're going to add 3 to 2 to get 5. And we keep on going backwards. So let's say I go, so A is kind of silly because it's only incident to D, so there's nothing really to choose here. We just have to add the processing time of A to the critical time of D to get 4. Same with C. You have to add 3 plus 5, that's 8. But now for B, what do I do here? Someone can tell me. Largest what? Uh-huh. Right, so good. So I'm going to pick the largest critical time. There are two times here that we're considering. We're considering the processing time, which is here, or here in this case. It's the number in the parentheses. And then there's the critical time. So we're going to add, well, here we're computing critical times. So we're going to add 5 plus 2 is 7. Right? And finally, we get down to this guy, start. And this is incident to all 3 of these. Choose the largest critical time, and we just add it to 0. So we're just going to get 8 here. So 8 is going to be the critical time of the entire graph. And each of these numbers gives us the critical time of the nodes. So what is the critical time? The critical time is the time that it takes to go along the critical path. It's the total processing time for the critical path, starting from that. Is it sensible? So if I look at this guy, A, for example, and I want to find its critical path, well, I can just, I go down, I go to the largest number incident to it, or incident. So I go from 4 to 3 to 2 to end. I just kind of go to the largest possible number down. And you can see that that has time 1 plus 1 plus 2, which is 4. Sorry? Yeah, we're going to do an example. We're going to do the example we did last time. I don't know about real life, but it's an actual example. 3 from, sorry, G. Which one?
Where did the 3 from D?
From D. This one. This guy? So, right. So, well, look at the, what is the critical path for D, starting at D? You go from D to G to N. That's the critical path.
So then it doesn't have to be like that plus G or anything.
What's F plus G? Yeah, this has nothing to do with F plus G.
Okay.
What I'm adding is 2 plus the processing time. It's still 2 plus 1, but I'm not adding, oh, I see. Yeah, maybe this looks a little like Pascal's triangle or something. I don't know. I'm not doing that. I'm adding, I'm taking the largest, I'm looking at D. I'm looking at the 2 things that D is incident to. I can draw all arrows down from D. I've got 2 possibilities. I choose the one with the largest critical time. That's this guy, not this guy. I've forgotten all about F. And I add that critical time to the processing time of D. That's 1 plus 2 equals 3. Okay. If you do this like 2 times with 2 different graphs, you'll be bored to tears, and then you'll realize you don't need to do it. You know, you'll know how to do it. This is not some kind of, I mean, we're not doing anything fancy here. But let's do a kind of one of these real life examples and see how that works. So I think what I was going to do is remind folks well, okay. Let's do a couple things. So this is how we get critical times. Now, as I said, once you have the critical times, you have your critical paths. Okay, you can write down your critical paths. And furthermore, there is an algorithm to write down a priority list. So this is the critical path algorithms. I think, oh yeah, that was the back. Okay, I forget the names of some of these. Critical path algorithm. This is very simple. The backflow algorithm, I think, is a little bit, you know, you just got to do it a couple of times. You'll know how to do it. Critical path algorithm is very easy. So once you do this backflow business, you'll get all of your critical times. You can see that you're now attaching new numbers to each of the tasks. So the critical path algorithm says, okay, use those numbers to make a priority list. With decreasing critical times. So before, with the decreasing time algorithm, we did it with the processing times. Now we're doing it with a different number, the critical time. And then 2 is make your schedule with this priority. Like 0 is find the critical times with the backflow. So we're gonna apply this algorithm to the problem we had last time. But before I do that, let's recall what we got with the decreasing time algorithm. We get a priority list there, which looked like the following. Well, we just went with decreasing time, so we went 5, 4, 3, I guess 3, either one. So let's go. Did I have this as, I think I did 2 for the. I don't care. So we have I, chapter 2, chapter 1. I'll just put it down this way. And I'm going to have this so I have another one. Okay. And we went ahead and scheduled tasks based on this list. So we schedule I first, and chapter 2. And chapter 3. But now we need, and even though the student was done at time 5, that student had to be idle because the bibliography has to wait until the chapters are done. Then we so this is what we got. It was not a very efficient algorithm, right? Or an efficient schedule, let's say. So now what we want to do is we want to do this with our new algorithm, critical path algorithm. So for that, we need to start by finding always need more room, I think. So we need to start by finding critical times. So we're going to do this backflow algorithm with this simple graph. You guys can all help. So there's nothing to do here. So at the next level, these are the 2 that we get. And what should I write for the critical times of these 2? 3 and 5, right? It's just their processing times because the critical path is just go directly to n. So for 5, you can see there's nothing going on. I mean, there's nothing really behind it except start. So I'm not going to worry about 5 for now. But now here for these guys, I need to consider the largest time next to it. So this one, what do I get for both of them? Okay, well, what do I get for each of them, I should say? 6 and 7, right? I did say 3 plus 3, 4 plus 3. And then at the end, I look, okay, so here's the only time where I have to actually make a choice. And 7 is the largest, so the processing time of the entire graph is 7. So sorry, the critical time of the entire graph is 7. Okay. So we get this graph. This is an important step that you need to accomplish first before going ahead and making the schedule. But now we can make a priority list very easily. So now when we make priority lists, we do not include start in a priority list. We just include all of the tasks. So what is the priority list? How should I start my priority list if I'm using the critical path algorithm? Sorry? Chapter 2, why? It has the largest critical time. Very good. So again, the task that has the largest processing time is the introduction. But now the chapter 2 in particular, has the largest critical time. So we're going to use, with the critical path algorithm, we use the critical times, not the processing times. So chapter 2 is right. Chapter 2 is first, then what? Chapter 1, then introduction, and then the bibliography. Okay, now that we have these, we have the priority list is a very simple thing to make the schedule. We just have to go down the priority list. So chapter 2 is ready. We can do it. So we'll assign that task to processor 1. Chapter 1 is ready. You can do it at time 0. So we'll assign that. Processor 2, or student 2, is available at time 3. And the next task up is the introduction, which we can do. It doesn't, it's ready, right? It doesn't depend on these things being finished. So we can assign introduction. And now at time 4, the student 1 or processor 1 is ready for another task, and we have the bibliography. And indeed, in this, now that we've done this correctly, or well done a nice algorithm, both chapters are finished, and we can indeed assign. Right. So, question. So how long did this, what is the time for this schedule? Total time? 8 hours. And what is the critical time for the graph, for the precedence graph? So, question to all of you. What can we do better? So if you look back in your notes, with this other graph, which was sort of not like based in real life, but it's kind of a good practice graph. We made a schedule with this, and we saw that the time that we got was essentially the time for the schedule we got. The best we could do, because it was indeed equal to the critical time of the graph. It was 8. So here you get a schedule that's 8 hours, which is not the time of the critical time of the graph. Is it the best we can do? Comment? Okay, so you would say no, and what you I didn't. So what are you saying no to? You're saying that this is the best you can do?
Well, I would say based on what you're saying about the other, that 8 equal to, then I would say, well, no, then that's not the optimal. But when you add the introduction or anything else, it's got to be 8 or higher.
I think that's a good argument, right? So you're saying it's got to be 8 or higher, right? But at the same time, what's going on? Why would we call, when we look at this number, why would we call this the critical time? What's so critical about it?
Because you have to have something done before it. Well, on I, it can be done on a third processor.
That's brilliant, right? So exactly. That time, if I add another student to the group, then this will be the minimal time. Like, in other words, and this is true for general setup. If you look at the critical time of your precedence relation diagram, if you have sufficient number of processors, then you can make a schedule that will be at that time. But you need enough. If you don't have enough, you get a longer time. Good job, guys. All right, so I'll send an announcement when I post the exam. I'm going to not do a homework this week. We'll just do that exam, and that's it. And we'll start working on the next section. Next, it'll be due on Wednesday, next Wednesday.
Thank you.
Yeah, have a good one.
Homework is still due by tonight.